We're happy to have Kevin Pilgrim from Indiana University, who's going to speak today about conformal surface embeddings in extremal length.
Thank you very much for the invitation. Merci beaucoup. This is joint work with Dylan Thurston and Jeremy Kahn, dating from several years ago. Our paper, a revised version, has been sent to the journal, and we are awaiting the final report, but it is on the archive. It's the up-to-date version. I'll spend just a tiny bit of time talking about some motivation from my area, which is complex dynamics, but then immediately not talk about dynamics at all, and focus just on a problem in complex analysis. Thank you, Maxime, so much for the kind invitation. I've enjoyed very, very much all of my visits to Montreal. My wife and I are hoping to vacation there sometime this August. So I work in dynamical systems, and one question that emerges from complex dynamics, meaning iteration of a complex analytic function, is something like this. Can we find two planar finitely connected domains, U and V, with U inside of V? In this diagram here, V is blue one and U is the red one. So V is a, I guess, hold sphere or two-hole disk, and U is a four-hole disk. And what I would like to know is there a pair of such domains where U maps in a 2-to-1 holomorphic cover onto V, with the outer boundary of U, this red curve. Wait, I can do this. No, that's not what I want. Where's my, oh, there it is. This red curve here, mapping in a 2-to-1 fashion here. This red curve mapping in a 1-to-1 fashion here, and this red curve mapping in a 2-to-1 fashion here, and this one mapping in a 1-to-1 fashion. The sort of mixture of analysis and combinatorics. And I would like that covering to be holomorphic. And so, sort of put another way, it's pretty easy to see. You can always do this using a smooth embeddings. And so what we're asking is a sort of question about whether sort of a Teichmuller space of these kind of things is non-empty. That's one way to think about it. So why do we care? Well, it turns out there's a technique called quasi-conformal surgery. And by applying this technique, you can actually extend this map of one domain to another to a quasi-regular map of the complex plane to itself. And then you can show it preserves a measurable complex structure, which you can straighten out using something called the measurable Riemann mapping theorem. And you can take this combinatorial picture and extract out of it a dynamical system, which turns out to be z²-1. So just a very, and the set of points where the dynamics is interesting for this map looks something like this. So this is just sort of where the motivation originates. But if we go back to this question, one can ask simply, when does one open finitely connected Riemann surface embed into another one holomorphically? So we will ask, the main question for today is, if R and S are Riemann surfaces, and we have an orientation preserving topological embedding, so a homeomorphism onto its image, but not necessarily surjective, when is this homotopic to a conformal embedding? Main question. Any questions so far?
I have a very.
Sorry, do you want the embedding to be proper?
Is this linked to Alfor's map and such?
I don't know necessarily what you mean by Alfor's map here.
A compact Riemann surface with boundary to.
No, here we're interested in embeddings. So these will be embeddings.
So they're not n-to-1. They're 1-to-1.
No, they're embeddings, right?
Okay. Then I misunderstood your first question. I thought it was 2-to-1 on the boundary.
Yes, but so here U is already a subset of V, but more abstractly, one could consider pairs of such objects where we have a covering map, say 2-to-1, which is holomorphic, And then we also seek an embedding, say phi, which is holomorphic. So if you find a complex structure on V, that determines a complex structure on U, and then our question is, when does U embed in V? We can kind of ignore this slide. It was just some motivation to explain a little bit of why I wanted to ask this question. But this question, I think, is of independent interest. For example, we know the answer if R and S are annuli. So one annulus embeds conformally into another if and only if the modulus of the domain is less than the modulus of the codomain.
Thank you. It's clear.
Before we forget, can you go back to the previous slide again? So the holomorphic map, the first one, yeah. So the map is a cover. Is that right?
The map pi here is a cover. Phi is just a holomorphic embedding.
So we should think of, if this comes from a dynamical system, you'd remove critical points and such. Yeah. Okay. There's no, I guess the question I want to ask is there a way to wiggle pi or to change pi, or once the homotopy class of the map is fixed, it's sort of, there's a unique choice of holomorphic map? Does my question make sense?
In this setting with open finitely connected surfaces, no, it's not unique. These Teichmuller spaces will not reduce to a point. So okay, so
repeat.
Even in this example, this sort of Teichmuller space of conformal structures and maps which satisfy these conditions will generally consist of more than a single element. I mean, we can just look at this picture, and you can imagine applying some holomorphic homeomorphism to the red subdomain, which just wiggles it a little bit, and we'll obtain another example.
I guess so. If you fix V, you said you wiggle it a little bit.
Well, I mean, just if you fix a conformal structure on V, that determines one on U.
Okay, yes, that was my question.
Holomorphic embeddings is more than just one point.
Okay.
It's more than just one map.
Thank you.
Okay, so just to set some terminology, today a Riemann surface will be denoted by either capital R or capital S, and throughout we'll focus on a compact surface minus a bunch of disks. And our general treatment also allows punctures. It complicates the statements a little bit, so I'm just going to pretend for today that there's just no punctures. So we can just think of Riemann surfaces are compact minus a bunch of disks. And I definitely want the boundary to be non-empty, at least in the Riemann surface R. So our main result is that a topological embedding, and here by using some classical theory, you can assume this map F is quasi-conformal. So such a topological map is homotopic to a conformal embedding if and only if a certain quantity that we call the stretch factor, so we call this a stretch, is at most 1. And the stretch factor is an invariant not of F itself, but of its homotopy class. And the stretch factor is defined to be a certain supremum of this ratio, where I'll explain the terminology here in just a moment. So in a second, I'm going to tell you what a simple multicurve is. I'll tell you this in a minute. But it goes like this. You take a simple multicurve in the domain, and you compute its extremal length. That's the denominator. And then you hit it with F, and you get another simple multicurve on S, and you compute its extremal length. And you take the ratio, and then you take the supremum over all such weighted multicurves. And that, by definition, is this stretch factor. And then there's a slight refinement of this, which we need in our applications, this map F is homotopic to what we call a strict conformal embedding. And strict means that the image misses an open set. And that is the case if and only if this stretch factor is strictly less than 1. This is the main result. And just a remark, well, the Schwartz lemma, Schwartz-Pick lemma, says that if you equip R and S, right, we have a Riemann surface R and we have a map S, and if this is holomorphic, well, we could put the hyperbolic metric here and the hyperbolic metric here, and then the Schwarz pick, right, implies that right, the size of this derivative in these hyperbolic metrics would be less than 1. So it would strictly decrease lengths of hyperbolic closed geodesics, for example. But if you try to make a corresponding version of stretch factor, then and make such a statement, then the statement turns out to be false. You can find homeomorphic hyperbolic surfaces with length decreasing embeddings, but which are not homotopic to holomorphic maps. And one case was done by Matsumoto, and then Maxime did the general case. Did I state this right, Maxime? So in some sense, this is kind of like a generalization of the Schwarz lemma. So okay, let's do a special case. There are two kinds of conformal geometers in the world, ones who like modulus and one who likes extremal length. Dylan likes extremal length, I like modulus. So I'm going to duplicate things. So what is modulus? You take an annulus, it's conformally isomorphic to a Euclidean cylinder. If you make the circumference 1, then the height is the modulus. And if you make the height 1, then the circumference is the extremal length. So they're sort of reciprocals of one another. And then because just to ground us, and this is a recycled talk from, or slide from one I gave in Beijing. So xiao is Chinese for small, and da is Chinese for big. So here is modulus is da, and here extremal length is da. So I actually tried to put petit and grand here, but I had a fight with my computer, and it just, I don't know why. I'm having sync problems or something. It wouldn't work. So let's look at a special case of this theorem that I already alluded to when the R and S are annuli. So suppose we have two annuli and we look at a topological embedding of one into the other, an essential one. So then when is this topological embedding homotopic to something conformal? Well, the modulus of the source, R, has to be at most the modulus of the second one. So there is no conformal embedding of this annulus into this annulus. Embed this one here, you have to stretch. So if you take this ratio, then this ratio would be so for the remainder of the talk, what I want to do is explain the statement in more detail, explain a little bit about the proof. And at the very end, I just have maybe one or two slides. There's a sort of additional statement about uniformity under coverings that's important in our applications to dynamics. Any questions so far? So what are simple multicurves? Well, they're things that look like this. So here's a 4-hole sphere. So there's one hole here, one hole here, one hole here, and one hole here. And a simple multicurve is a collection of curves up to isotopy, which looks something like this. I might have a couple going over here and maybe 3 going over here. And these are the kinds of things that we call simple multicurves. And we'll denote them by capital Roman letters, C, and denote the homotopy class or equivalence class under free homotopy and reparametrization by these square brackets. So I'm allowed to wiggle these around, and they can even cross each other and so forth. Okay, so if you have an inclusion of one such surface into another one, then there's an induced map on multicurves. But you might have to erase some inessential pieces. So here is a 4-hole sphere including into a 3-hole sphere. Sort of this surface has a cap on this hole, and this component over here, when you include it into S, now is inessential, and so I can contract it to a point, and so I would simply just eliminate that. And so we have to delete components of multi-curves that are inessential. So there's a induced push for it. What is extremal length in this context? So if we have a Riemann surface, then equivalently, it's a class of conformal metrics. So we can pick boldface G, a conformal metric on this Riemann surface. And if we have a multi-curve, capital C, and what we call a sort of test function, then we can do the following. So this is this quantity over here is sort of the shortest in row G of C. So C, after all, is a bunch of curves. If I had an honest conformal metric G, then I could imagine measuring the length with respect to G of every one of these components. And then I could vary over the isotopy class and try to make them as short as possible. And the extra thing I'm doing is that I'm allowing a weight function in front here, which is only really required to be measurable. So it could be 0 on open sets. But it still gives me a density, and we can integrate with respect to arc length. And we take the infimum over representing curves in the same way as if we had an honest metric. And that's this quantity capital L that appears in the numerator here. So we square that, and then we divide by the area. What is the area here? This area is just, so this area is just integral of rho G squared dA over R. So just the usual area, again, thought of where we've weighted it by this function rho. So if R is a rectangle or an annulus, this is the ordinary definition of extremal length. When you use, say, the family of curves that connect a pair of opposite sides or that go around the annulus.
Sorry, just a detail. The G should be in the dA, no? It's the metric, right? Definition of the area, the integral.
Yeah. Okay. Sure.
Thank you.
Okay.
I think he means that the G is already accounted for in the dA, so that it
Yeah.
shouldn't be squared.
Yeah, G
So
is
it's
not
just
the
the
function.
Well, okay, so I think there's this has come up with my graduate students too. So I mean, is this a metric? This is a metric for me. So maybe you would say that this is a metric, in which case we don't need the square.
I just mean that G is a function, or is it a metric? So I mean, perhaps it's not important for the talk. I don't want to.
Yeah, no, I guess, okay, so there, okay.
Sorry about this.
No, it's okay. It turns out that there's a basic result in the subject that says that this supremum is actually realized by a unique such metric up to scale given by a so-called quadratic differential. So I should say what a quadratic differential is. So when I was a graduate student, it made absolutely no sense to say that a quadratic differential was a section of a square of some canonical bundle or something like that. Only like 20 years later did I learn that a much easier way of thinking about a quadratic differential is an expression of your Riemann surface as a union of a bunch of polygons in the Euclidean plane, where you glue the polygons by translations and plus or minus. This was a much more down-to-earth understanding of what a quadratic differential on a Riemann surface actually is. So I'm not going to go into too much detail, but it's essentially a way of turning your Riemann surface into a Euclidean object outside of a finite set of points, which are the zeros of the quadratic differential, and maybe the poles. And we're exclusively concerned with quadratic differentials with some special properties since our Riemann surfaces have boundary. We want the boundary components of our Riemann surface to correspond to horizontal trajectories of this quadratic differential. And I'll illustrate that with a picture. So let's make a Riemann surface out of 2 copies of this planar domain. So the planar domain I'm looking at is this stuff here. And I'm going to take 2 copies of this and glue it together. And so how am I going to glue it together? I'm going to glue this side to this side by a translation, horizontal translation, this side to this side by a horizontal translation, this side to this side by horizontal translation, this one to this one. But then here I have to use a combination of a horizontal translation and a 180-degree rotation. When I do that, I will get something which topologically is a pair of pants. Something like, oops. So this top boundary component, there'll be 2 other components here. Something like this. This goes up, something like that. And it's a little hard to draw, but. And then the quadratic differential given by just dz squared, where z is the coordinate in the complex plane here, will be well defined. Because dz is well defined, dz kills translations, and then the square kills the minus sign for the rotation. So this expression dz squared is then well defined on this quote. And when you have a quadratic differential, you have these natural Euclidean coordinates. So we have this notion of horizontal, and notice that these boundary components here are indeed correspond to horizontal lines. So these are the types of quadratic differentials we're thinking about. The Euclidean structure is slightly singular. So this point right there, if you flatten things out, you'll see actually not 2 red curves coming into it, but 3 because of the way we've glued things up. And so that's a 0 of order 1 of this quadratic differential. So there are finitely many horizontal leaves of this foliation by horizontal curves, which are mildly singular in this way. Any questions?
Are you saying that all Riemann surfaces are represented in this way, in a similar way, or like all quadratic?
Certainly finite type Riemann surfaces. So on compact Riemann surfaces, for example, the space of holomorphic 1 forms is G complex dimensional on a Riemann surface of genus G. There's a similar formula that counts the dimension of the vector space of finite area, that is integrable quadratic differentials, on Riemann surfaces of higher genus. And then if you start allowing poles at punctures and you have some constraints on the boundary curves, and there's another formula that counts this dimension. I don't know if I know the general answer for genus G minus D disks minus N punctures. With horizontal boundary components, there's a formula for the dimension of the space of finite area such things. So as I mentioned, when we have a weighted multicurve and we compute its extremal length, that extremal length is a quantity which involves a soup over such metrics, and there's a unique extremal such metric. And it turns out that by a theorem of Jenkins and Strabel, it always comes from that metric always comes from a quadratic differential. So the statement of the theorem is if you have this simple multicurve, finitely many closed curves up to homotopy, then there's a unique Jenkins-Strabel extremal metric given by a quadratic differential, which decomposes, where the horizontal leaves decompose your Riemann surface into Euclidean cylinders, and their heights are 1, and the extremal length is then just the area of this Riemann surface with respect to this quadratic differential. And there's a mild generalization where you put a non-negative real number in front of every component of this multicurve. If we go back to this sort of picture, so I could represent this situation where this has two blue things, but I could have drawn one, and then I could have put a weight 2, weight 3, and weight 1 here. So those would be weighted multicurves. The weights take into account sort of the number of strands, but it turns out you can make sense of this even for just arbitrary non-negative weights. And so here's a concrete example in the Riemann surface I just mentioned, this sort of pair of pants. So here we have one component here, which I'll call, I guess, yellow is a C1 and blue is C2, and this is C3. And I'm going to put weight 15 here and 7 here and 9 here. Then I'm going to double this over its boundary as I just illustrated. And then I'm going to ask, what's the extremal length? The extremal length is just the area. So the extremal metric just turns out to be the one induced by dz squared on the Euclidean plane. You can count these squares 1, 2, 3, 4, 5, 6, 7, 8, up to 15. And so that will be the unique metric, and the extremal length is then just twice the area of this polygon. In our applications, though, we need a version of extremal length which involves an inf rather than a sup. This makes making estimates very handy, because then if we want an upper bound, we just look for metrics, and if we want a lower bound, we have this other characterization as an infimum. The proposition is that the extremal length is an infimum over all conformal embeddings into our Riemann surface, but we're allowed to vary the conformal structures on this disjoint union of annuli. Somehow the idea is if I want to know the extremal length, say of this curve on a surface of genus 2 going around, what I do is I look for an annulus A, and I embed this conformally, which I can certainly do a little bit, and then I try to make this annulus as fat as possible. So this will fill out more and more and more, and then the maximum modulus of a conformal annulus that I can fit in this homotopy class is the reciprocal of the extremal length. And the proof is fairly straightforward. The extremal is realized by a quadratic differential, and we use the theorem of Strabel, and we have a generalization with weighted multicurves. So armed with this, we can easily prove necessity of our main result if the embedding is homotopic to a conformal map. And here, my notation is in conflict a little bit. This is now a map, not a metric. So if F is homotopic to a conformal map G, then the stretch factor is at most 1. And the reason is that there are more such conformal structures on the image than there are in the domain, because if I have one Riemann surface and I'm embedding it into some other Riemann surface. So maybe this one is coming in over here, and I have a curve and an annulus, and I try to make this annulus in here as fat as possible. If I then put this surface into a bigger surface, then there's simply a greater possibility for making this image over here larger. And so it's just a tautology. It comes exactly from the definitions. There are more conformal structures on the image over here. And so by this previous result that says extremal length is an infimum, if I have more conformal structures to work with, then the infimum goes down. And so this ratio will be less than 1. Pretty easy. Any questions there? The sufficiency is harder. So now we want to show that if this stretch factor is at most 1, then our map is homotopic to a conformal embedding. And here we're going to make crucial use of a theorem of Ioffe from the 1970s that says, well, if you're not homotopic to a conformal map, then there is, in some sense, an embedding which minimizes distortion in some way. So you might, if you are familiar with Teichmüller theory, if you have two homeomorphic Riemann surfaces, say we have one. Actually, let me do the even more classical example. Let's say I have two annuli. Whoops. If I have this annulus and I have this annulus, so there's no conformal embedding here, but there's basically a unique sort of linear stretch, which minimizes the so-called quasi-conformal dilatation among maps from this Riemann surface to that Riemann surface that just stretches affinely. And this Ioffe theorem is a generalization of this observation. So what is formally, what is a Teichmüller embedding of one Riemann surface to another? It's a map from R to S, but then we also get a quadratic differential Q on S and a quadratic differential Q prime on R. And remember, a quadratic differential gives you local Euclidean coordinates. And so we have a map now between two surfaces equipped with local Euclidean coordinates, so we can look at the expression of that map in those local Euclidean coordinates. And a Teichmüller embedding is one where this local expression is just a horizontal stretch by some factor k bigger than 1 in the x direction. So that's one condition to be a Teichmüller embedding. And the other condition is that the image has to be the complement of finitely many horizontal slits. Here is an example of a Teichmüller embedding G. The Teichmüller embedding G will be this. So on the left here is an annulus, and I've drawn it as a right Euclidean annulus, and this is meant to represent. So I stretch by some factor k in the horizontal direction. So here I have two coordinates x and local Euclidean coordinates x and y, and this goes to kx y, some k bigger than 1. And now I have a wide annulus with this horizontal slit, and I just include this by kind of erasing the slit. Think of this as like erase the slit. And so this composition is what we call a Teichmüller. A little bit of a warning though, not every quadratic differential is Jenkins-Strabel, and it's easy to manufacture examples of such scenarios where the extremal quadratic differential in Ioffe theorem, where those quadratic differentials are not Jenkins-Strabel. So let's take our Riemann surface to be S, the target to be a torus. So just there's a S, right? So I'm going to glue, this to this. The ordinary Euclidean square torus, and then the Riemann surface R is going to be this torus minus an interval J. So R is equal to S minus this interval J. And how do I choose J? Well, I take this 2x2 matrix, which is an automorphism of this torus. It's not conformal, it's affine. So here this is a map F, which is a homeomorphism. It's an embedding, and it takes this red interval to a longer red interval. So this is f of j. And so here is well, I guess I should have called this G. So here this is a Teichmüller embedding. This in natural Euclidean coordinates, if I rotate the picture, so that this direction is horizontal, this will be a Teichmuller embedding. But the leaves of this quadratic differential are now not closed. They're lines of irrational slope. So it's a little more complicated. So what is the intuition for the sufficiency? Well, if our topological map is not homotopic to a conformal map, Ioffa's theorem gives us a Teichmuller embedding and quadratic differentials on domain and codomain, which make our Teichmuller embedding look like this stretch. And if the maps involved were actually homomorphisms, we would be done, because then the extremal length of f of c and the extremal length of g of c would be the same, because f and g are homotopic. So as sets of curves, these sets of curves would be the same. And then since G is just a stretch, the effect of how stretch maps change, horizontal stretch change extremal length, that just the factor of k just pulls out. That's an easy calculation, right? The modulus of an annulus just stretches by that factor k if you make it k times as tall. And then if you take the ratio, you pick up exactly this factor of k, which from Ioffa's theorem is bigger than 1. And that's a contradiction. So this is what we'd like to do, except that we can't quite do that. And so what saves us, here Dylan's background in surface topology was actually crucial to move this project forward. We have to approximate quadratic differentials where the horizontal foliations are not necessarily closed by things where they are closed. And there's a classical theorem to that effect. So basically, I mean, what we're saying is that a line of slope root 2 is approximately a line of slope 1414 over 1000. And so just in the way that we can approximate root 2 by this, we are going to be able to approximate the quadratic differentials from Ioffa's theorem by quadratic differentials coming from weighted multicurves. And that takes us a step closer to our definition of stretch factor, which is where we want to go. So the theorem we need is something that's now called the Heights theorem, to Hubbard and Major. We let MF plus of S be this set of measured foliations on the target surface S, which are tangent to the boundary. There's a natural topology on this space, and it turns out to be homeomorphic to a ball. Quadratic differentials give examples of elements of this space by taking the horizontal measured foliation. And then it's a fact that the foliations from Jenkins-Strabel quadratic differentials are dense in this space, and that this notion of extremal length of weighted multicurves extends continuously to the entire space of measured foliations, where now the extremal length of an arbitrary horizontal measured foliation is just, again, the area. But a subtlety here is, in our setting, is that when we look at these embeddings of one surface to another, they don't induce continuous maps on measured foliations. And so I want to mention something about that. So if I take a 4-hole sphere and include it into a 3-hole sphere, so here the set of all curves C is basically like the rational numbers union something like in 1 over 0. So you can enumerate all simple closed curves, like ones like this and ones like this, and more generally. So there's a 1-to-1 correspondence between such curves and rationals. But on the 3-hole sphere, the set of such curves just consists of this guy, and this guy. There's only 3 of them. And this correspondence is, if you do this right, it has something to do with slope. And then which curve you go to. If you start with P over Q, you go to either you go to one of 3 things, and it's something like even over odd, odd over odd, or odd over even. So you can have two rationals that are very, very close, but go to different elements depending on the parity of the numerator and denominator. So this is meant to show a discontinuity. So the conclusion of the proof of sufficiency goes something like this. Again, we're assuming that we're not homotopic to a conformal embedding. So E-office theorem gives us this Teichmuller embedding, as well as two quadratic differentials, one on the source R and one on the target. And then the key lemma that we use is our ability to simultaneously approximate the corresponding horizontal foliations by weighted multicurves. So we can find weighted multicurves on R, whose such that if we regard these, if we look at the corresponding Jenkins foliations given by the Jenkins-Strabel quadratic differentials, those approximate the horizontal foliations of Q prime given by I-office theorem, and similarly their images approximate those given by Q. And so then when we compute this, the stretch factor of F will by definition, it will be this, it will be at least this limiting ratio because the stretch factor is a supremum. And by continuity of extremal length with respect to this topology, the numerator and denominator approach the extremal lengths of these foliations. And then the Heights theorem that I cited before says these extremal lengths are just the areas, but then the areas change by this factor of k because we have a Teichmuller embedding. And so that gives the proof of sufficiency. Any questions? So as I mentioned, the main theorem has a refinement about strictness, namely that we can arrange that our image miss an open set if and only if this stretch factor is strictly less than 1. And so what's the proof? Well, when we look at quadratic differentials on the target, if I look at this ratio of area of the image over the area of the whole space, that as a function on quadratic differentials, this quantity, this ratio, doesn't depend on the scaling Q. If I multiply Q by 10, that cancels. And so this becomes a continuous function on a real projective space, or on the projectivization, and that's a compact set. Quadratic differentials are a finite dimensional space. If I projectivize, that becomes compact. So I have a continuous function on a compact set. And so there will be some maximum value less than 1 that this ratio can be. And so if I take any simple multicurve and look at the corresponding Jenkins-Strabel differential when I move it over to S, I can pull back that extremal metric and do this calculation. And I notice that again, on S, the surface S is bigger than the surface R, so there are more curves. So we have this inequality, and then it follows fairly straightforward from the definitions that our stretch factor will be at most 1. So this gives one direction, that gives the necessity. If we miss an open set, then this fraction has to be less than 1. And so the stretch factor is less than 1. And conversely, if the stretch factor is less than 1, I can actually make my Riemann surface ever so slightly larger and preserve the stretch factor being less than 1, simply by stretching a tiny bit along these Jenkins-Strabel, by stretching in this other direction. And that means that I can add tiny little collars, so that if this surface embeds into this one, then this slightly larger surface will embed into this one. And so that gives the strictness. And I think are there questions here?
So that means that if you miss an open set, then you can change the map. You can still conformally embed and miss an open set, like a neighborhood of the boundary. Is that right?
That's right.
Okay.
That's right. Yeah, so this actually shows a little bit more. If you miss an open set, then you can actually arrange so that you still have a conformal embedding which misses a neighborhood of the boundary.
Thank you.
Because you just take your original surface in your domain, you add on these red collars by stretching a tiny little bit that keeps that stretch factor less than 1. You embed that thing, and now you've missed the image of the red collars. So I think I can't say too much here. The setup here is that we have R and we're trying to go into S, and in applications we might have a cover, S tilde, some cover. And then anytime you have a pair of maps like this, you can complete the diagram and get some sort of R tilde, which will be embedding into this tilde. And then you can ask for the stretch factor here and the stretch factor here, and you can ask how these stretch factors compare. And they can go up, but they can't go up too much. And that's one result, namely we could take all possible finite covers as tilde, and we could take a soup of stretch factors over all such finite covers, and we get something we call a lifted stretch factor. And then the theorem is that if our original stretch factor is less than 1, then so is this lifted stretch factor. And that's not obvious at all. Jeremy Kahn was very helpful to us for this part of the problem, and I don't think I'll be able to say anything intelligent about the proof there in the remaining minutes, and so I'll stop there. Thank you.
Thanks, Kevin.
I want to just, can one ask similar questions, let's say in 3 dimensions? I mean, the answer will probably be very different, but you have like 2 manifolds and the boundary, and you can try to embed them.
So our focus was on conformal maps, and conformal maps are significantly more rigid in higher dimensions. In dimensions 3 and above, every conformal map of Euclidean space is a restriction of a Mobius transformation. So it's profoundly more rigid a setting. And so I don't know what kind of directions one could ask. I mean, certainly with other kinds of structures like symplectic, right? I mean, that's a deep theorem, like looking at homotopy classes of symplectic maps of one manifold to another. I mean, that's a whole industry, I think. Here, the focus is really on conformal.
Just to add to that, this theorem that you're proving is an instance of an H principle. Like, it's a characterization of when you can realize like a map in a certain family of maps.
I guess you're right. Yeah.
Maybe a technical question about this simultaneous approximation by multi-curves. Can you say how you get around the discontinuity of the map to get this?
Pages and pages and pages of technical details. This is all Dylan, involving train tracks. So there is an elaborate theory of how train tracks can be used to encode limits of simple closed curves on surfaces. And it boils down to understanding how train tracks behave in this setting. So I can't really say too much there.
So you still use F to sort of map one train track from one surface to another, and then you use like this train track to cleverly to approximate. Okay.
Yeah, see, so somehow this discontinuity I mentioned, like you have to show that, well, that might happen on some, like see, we don't need continuity everywhere. We only need continuity at this foliation given by Eoffus theorem. So we just have to adapt, you know, we have to show in some sense that this embedding is going to pick out train tracks on R and S that carry the things that we need them to carry. We don't need them to carry everything. We just need to carry the things that we care about.
Okay, thank you.
Sure.
Any other questions or comments?
For infinite surfaces, this is a more difficult question.
So at the very beginning, I cheated and I said that topological embedding was the same as quasi-conformal embedding. In other words, if you have finite type Riemann surfaces, then there's a topological embedding of one into the other if and only if there's a quasi-conformal embedding of one into the other. And we have to rule out, you know, like punctured disks and annuli, right? There's no quasi-conformal map from a punctured disk into an annulus, which is essential. So if you ignore those types of counterexamples, then there's some classical theorems that you can cite about a smooth approximation, and then on compact sets, smooth things are quasi-conformal and so forth. This was actually very annoying. We had to go digging in the literature to find this. But if you go to Riemann surfaces of infinite type, this is no longer true, because you can have a Riemann surface of infinite genus, and you can make the disconnecting curves have hyperbolic lengths that are, you know, smaller and smaller and smaller and smaller, and that will be homeomorphic to a Riemann surface where those geodesics are all the same length, for example, but there'll be no quasi-conformal map that sends one to the other. So you can't really even get the setting off the ground.
I see, okay.
Infinite genus without making some tameness restrictions on the geometry.
But on the very first slide, you had like a diagram of one domain inside the other, and then you were specifying which boundary map to which by what degree. And then you said, like, you can do this topologically. So in general, if I draw a picture of two domains like this, is there, like, is there a topological characterization of when you can realize this by a holomorphic cover?
Yeah, so that's actually a great question. So this is the first step in a larger program that Dylan was thinking about. And so if I look at this formula z squared minus 1, this is a holomorphic map of the Riemann sphere to itself, and it has a certain finiteness properties. It has two critical points, one at 0 and one at infinity, and the forward orbits of those critical points form a finite set. And William Thurston characterized such so-called critically finite rational functions among the larger class of sort of topological maps with these properties. So you take z squared minus 1, you mark the 3 points 0, minus 1, and infinity, and then you look at all branched covers of degree 2 homotopic to z squared minus 1. You can look at such abstract homotopy classes, and you can ask, is there a rational representative and William Thurston gave necessary and sufficient combinatorial criteria, but it's a negative characterization. It says that you are rational if and only if you do not have obstructions. In contrast, for a restricted class of these guys, Dylan has what's called a positive characterization. You are equivalent to a rational map if you can find, well, basically a picture like this, except that Dylan's characterization allows for a graph theoretic interpretation of this. So you could imagine that this red domain is homeomorphic to this, but it's very, very skinny. So I could have drawn the red domain, the big one, like, or sorry, whoops. I could have drawn the red domain something like this. And I could have drawn the blue domain V as something like this. And so we can almost imagine a sort of limit of this situation where I have a pair of maps of graphs. I have a covering map of a graph, and I have some sort of continuous map, now no longer an embedding, but just some sort of continuous map, which sort of collapses this thing. And Dylan has a theory of energies of graphs when equipped with length metrics. And there's a kind of L2 energy or embedding energy. And that energy has a stretch factor, and if that stretch factor is less than 1, then he shows that you can actually thicken these graphs to Riemann surfaces that look like this. And then this theory of embeddings of graphs and energies captures when this is possible. But that's like a second talk, how that works.
Thank you.
Thank you again for the invitation. It's a pleasure to meet you.